Hello, you're welcome back. All right, so we'll continue from where we stop. Okay, so we're gonna look at some other standard derivative. Okay, the one I've not actually given you. Now, this is basically on trigonometrical function. All right, so now let's look at the standard derivative of sec x. Okay, so the standard derivative of sec x is given as sec x tan x. Of course, you can prove this using quotient rule. Okay, you can try it because sec x is always equal to 1 over cos x. So if I should use quotient rule now to prove this, that simply means that my u is 1 and of course my v is cos x. So you cannot do divide x, which of course is going to be equal to v cos x, then multiply by the derivative of 1, okay, which is 0. Then minus, now keep 1 constant to 1, then I find the derivative of cos x, that is minus sin x. Okay, then divided by cos square x. So this now gonna be, this is 0 already, and of course minus times minus is plus. So I'm having sin x, okay, sin x all over cos square x, cos square x. So this is gonna be equal to, of course you know that sin x all over cos x, sin x all over cos x, because I can split this into cos x times cos x, right? Cos x times cos x. So which of course now is gonna give me sin x all over cos x, that's tan x, and 1 all over cos x is sec x. So you can see all this derivative of trigonometry has proof, right? So that's why we have y being equal to sec x, then dy dx is equal to sec x tan x. For cot x, dy dx is minus cosec x. Then for cosec x, dy dx is minus cosec x cot x. So you just take note of all this standard derivative of trigonometry. Now when you have y raised to the power of ax, the a here represent this not exponent, okay? Please take note of that. This is the a is actually a real number, okay? A raised power s, then divide s is as ln a. So invariably now if I have y to be equal to 2 raised to the power of x, then divide the x, divide the s is going to be equal to 2 raised to the power, the 2 raised to the power x, then ln 2. Okay, so please take note of that. So we're going to solve more questions in this video, then after which we'll look at the application of derivative. Okay, now let's look at a typical example. All right, let's look at the derivative of y being equal to a trigonometrical function, pardon me, a polynomial, okay, polynomial function. So let's say you're being asked to find the slope, find the y dx, okay, find the y dx at x equal to 1. So now first of all I have to find the y dx of that solution before I now substitute x being equal to 1. Now what's the dy dx of that polynomial function? Of course you know how we used to find the dy dx of the powers of x, right? So for the dy dx of x raised power 3, that's gonna be x raised power 3, then of course minus 1, then the 3 comes at the back. Okay, that 3x raised to the power 3 minus 4, you know that already. This was going to be 2, the 2 comes to the back, right? 2 times 2 raised to the power x, 2 minus 1. That's 1 here, the 1 comes at the back. 1 times 4 is 4, right? That's x raised to the power 1 minus 1, okay? The derivative of a constant is 0. So this is going to be equal to 3x squared minus 4x. Okay, then of course plus 4. So at this particular point now, it is now easy for me to find the derivative. Okay, I've already gotten the derivative, the function of the derivative now. So I need to actually get the value of the derivative at the point where x is equal to 1. So at the point when x is equal to 1, okay, so that's gonna be, the derivative is gonna be what, 3 into 1 cube minus 4 times 1, then plus 4. Okay, so this is gonna give me 3. 1 cube is 1. 1 times 3 is still 3. 4 times 1 is 4. Then of course plus 4. So that gives me minus 4 plus 4, that is 0. That gives me 3. Okay, so I hope that is well understood. Okay, so now let's look at the basic application of derivative, okay, differentiation. Now there are a lot of application of differentiation, but I'm just gonna pick, okay, few, just gonna pick 2. So one application we are gonna be looking at here in this tutorial is, okay, the turning point, which of course include either maximum or minimum. Okay, maximum or minimum value of a function. Then we'll look at the rate of change. So let's start with the very first. Okay, so let's look at the stationary point, the maximum or minimum point. Okay, now that's maximum or minimum value of a function. Now a function actually attains its maximum or minimum value, okay, at the maximum or even minimum, okay, value or minimum point of that particular of a function, then divide the x at that point is always equal to 0. Divide the x is equal to 0. Now let's look at a typical example, okay, a typical question. For example, you are being asked to find the value of x okay at the minimum point, at the minimum point of y equal to x squared minus 2x. Okay, so solution. So at y equal to x squared minus 2x. Okay, so if at the minimum point of this particular function the dy dx is equal to 0, okay, dy dx is equal to 0 at minimum point. So now, having known that, now it is now easy for me to actually get my x, because I have to find dy dx. Okay, so now let's find dy dx of this. Of course, if I differentiate this, that's going to give me 2x. If I differentiate minus if I differentiate minus 2x, I'm going to have 2. So of course dy dx is equal to 0, right? So I can now find x. So of course, for me to find x now, x is going to be equal to 2 all over 2, which gives me 1. So that is just basically the minimum what, okay, how we are get to find the minimum or the maximum value of a function. So having gotten the x to be equal to 2, now assuming that I'm being asked to find the minimum value of this function. So the minimum value of x is 1. So the minimum value of the function is gonna be, okay, if I put substitute x being equal to 1 into this function. Okay, so that is it. Now let's now talk about the rate of change. Rate of change. Okay, now when do we apply rate of change? We apply rate of change, okay, if of course we have a function, let's say y being is a function of u. Y is a function of u. Then it also happen that u now, y is a function of u, and u now is a function of time. U is a function of time. So it's possible, okay? So to have y depends on u, and u depends on t. So we apply rate of change anytime we have this kind of function of a function, okay? So now of course, for us to be able to get our, if I want to now find the y respect to the t, the change in y with time, okay, of course I have to apply chain rule. So if I want to find the change in y with respect to time, okay, I have to apply chain rule. And of course, remember chain rule. So that means for me to apply chain, I'm going to do the change in y, please pardon me. So I have to do change in y with respect to u. Then I now multiply it with change in u with respect to time. For example, let's look at example. Okay, area of a circle. Okay, the question goes this way. Find the rates. Find the rate of change. Find the rate of change in the area. In the area of a circle. Okay. if its radius changes at 5 centimeter. Okay. Okay, let me do this. Okay, I'm not giving the radius of the circle. So it goes this way. Alright, so now I'm having of radius of a circle of radius 7 cm. Okay, if its radius changes at a rate of 5 centimeter per second. So now this is a typical example of rate of change. So we are now being told that, of course, we are dealing with area of the circle, right? So of course the area of a circle is a function of its radius. Area of a circle is given as pi r square. So I'm asked to find the rate at which the area changes with time. Okay, so remember, this is a function of a function. The area is a function of time. Okay, while the area is a function of a radius. Okay, while the radius now is a function of time. So applying chain rule here. So the change of area with time is going to be product of the rate of change of area with the radius, the ADR, then times the rate of change of the radius with time. Okay, so that's chain rule. Now let's do this. Let's differentiate A with respect to R. Okay, this is R square. Of course, you know how we differentiate that. 2 comes at the back. Of course, this pi here is a constant, so I will now have 2 pi. Okay, then r raised power 2 minus 1, which of course is 1. Okay, so if I differentiate pi r square, I have 2 pi r, then multiply by the r dt, the change in radius with time, and that was given in this question. Okay, the rate of change of radius with time, the radius changes at 5 centimeter per second. So that is what I'm going to write here. Okay, so if I multiply this to 2 times 10, that's going to give me 10. That's going to be 10 pi r. So I was also given the radius. Okay, the radius I was given 7. 7 is the radius. I'm having 10 times the pi is 22 all over 7, then times the radius 7 cancels 7. So at the end of the day, now the area actually changes at 220 centimeters square. Okay, then per seconds. So that is rate of change. Okay, so please take note of that, and we are going to apply some other technique to solve derivative of other function, and we'll do that in the next video. All right, see you in the next video. Thank you very much.